Right now, as you watch this video, Earth is moving through space at nearly 67,000 miles per hour. Not the rockets, not the satellites, the entire planet. Every second, all of us are flying sideways around the sun at a speed so extreme that if it suddenly stopped, the oceans would keep moving, the atmosphere would continue racing forward, and civilization itself would collapse instantly. But here's the strange part. Even after sending spacecraft to every planet in the solar system, even after landing robots on Mars, even after photographing Pluto from less than 8,000 miles away, there is still one direction humanity has barely explored. Not outward, not toward another planet. Up. Directly above and below the sun, a direction so difficult to reach that traveling billions of miles to Pluto actually requires less energy than escaping vertically out of the flat disk our planets share. And the reason why changes the way you understand space itself. Because the truth is, the solar system is not built like the diagrams you saw in school. It is a prison of motion, and escaping it may require one of the most dangerous maneuvers ever imagined by human beings. A maneuver where a spacecraft must first fall toward the sun before it can ever hope to rise away from it. This is the forgotten direction of the solar system, and what waits there may completely change how humanity sees its place in the galaxy. To understand why this journey is so difficult, you first need to understand something almost nobody thinks about. You are already moving. Right now, even if you are sitting completely still, Earth is orbiting the sun at roughly 30 kilometers per second. That's around 67,000 miles per hour. Every human being, every city, every ocean, every satellite is already locked into this enormous sideways motion around our star. And every rocket launched from Earth inherits that speed automatically. When NASA launches a probe toward Mars, the spacecraft doesn't start from zero. It already possesses Earth's orbital momentum. That's why traveling between planets is surprisingly efficient. Mars, Jupiter, Saturn, Neptune, they all exist within roughly the same flat plane around the sun. Astronomers call this the ecliptic plane, and because everything moves within this giant cosmic disk, spacecraft can simply slide across it with relatively small adjustments in speed. That sideways motion becomes a gift, a shortcut, a free boost provided by Earth itself. But the moment you try to leave that plane, everything changes. Imagine driving 70,000 miles per hour down a highway, then suddenly trying to move straight upward into the sky. That is essentially the problem. To travel directly above the sun, a spacecraft must first cancel the massive sideways velocity it already has, and that requires an absurd amount of energy. Mission planners measure this using something called delta V, the amount of velocity change a spacecraft must create using its own fuel. Reaching Mars from Earth orbit takes roughly 4 kilometers of delta V, but escaping vertically out of the solar system's flat plane can nearly require 30 kilometers, almost 10 times more. That is why humanity has explored the solar system sideways, but almost never vertically. And it leads to one of the strangest truths in all of astronomy. Traveling billions of miles outward to Pluto is easier than climbing a relatively short distance above the sun's poles. The physics sounds backwards, but space itself does not care about intuition. It only cares about momentum, and momentum has trapped us inside a flat rotating disk for billions of years. Because almost no spacecraft have escaped upward, the regions directly above and below the sun remain one of the least explored frontiers in our entire cosmic neighborhood. Which is astonishing when you think about it. We have detailed maps of Mars, we've landed probes on comets, we've photographed distant moons orbiting Saturn and Jupiter, but the poles of our own sun, the closest star to Earth, remained almost completely unseen until very recently.
And those regions may be the most important parts of the sun itself, because the sun's poles are where massive magnetic changes begin. Every 11 years, the sun flips its magnetic field completely. North becomes south, south becomes north, an event so violent it reshapes the entire solar weather environment of the solar system. Solar storms, radiation bursts, solar wind, all of it is connected to processes occurring near the poles. And yet, for decades, humanity observed the sun almost entirely from the side, like trying to understand Earth's climate while only standing at the equator. There have been only 2 real attempts to solve this problem. The first mission was Ulysses, launched in 1990 through a joint partnership between NASA and the European Space Agency. But even Ulysses could not simply fly upward. Instead, the spacecraft had to perform an extraordinary detour. It traveled all the way out to Jupiter first, then used Jupiter's gravity like a giant cosmic slingshot to bend its orbit nearly 80 degrees out of the planetary plane. The maneuver worked. For the first time in history, humanity measured the fast solar wind streaming from the sun's poles. But there was a limitation. Ulysses carried instruments from the 1980s. It had no advanced imaging system capable of photographing the poles directly. We measured them, but we still never truly saw them. That changed recently. In 2025, the European Space Agency's Solar Orbiter mission sent back the first direct images ever captured of the sun's south pole. The photographs shocked scientists. Instead of a calm, smooth region, the pole appeared tangled, chaotic, and magnetically violent, a landscape of twisting plasma and unstable magnetic structures unlike anything visible from Earth. Think about that for a moment. Humanity reached the moon over half a century ago. We photographed Pluto. We landed on Mars. But until last year, nobody had truly seen the top or bottom of our own star. But there is another reason this vertical journey matters, and this reason may be even bigger. We do not actually know what our solar system looks like from the outside. Surrounding the sun is an enormous invisible bubble called the heliosphere. This bubble is created by the solar wind pushing outward against interstellar space. Inside the heliosphere exists the planets, the asteroids, the comets, and every human spacecraft ever launched. Outside it lies the true environment of the Milky Way galaxy, a region flooded with interstellar particles and dangerous cosmic radiation. For decades, scientists believed this bubble looked like a comet, rounded in the front, long trailing tail behind it. But newer studies suggest that picture may be completely wrong. Using NASA data and advanced simulations, researchers now believe the heliosphere may resemble something far stranger, more like a distorted crescent with twisted jets extending outward. And there's a problem. We still can't confirm its real shape, because no spacecraft has ever traveled far enough above the solar system to look back down at it properly. Voyager 1 and Voyager 2 crossed into interstellar space, but both exited sideways through the planetary plane. Useful, but limited. To truly understand our place inside this galaxy bubble, humanity may eventually need a spacecraft capable of climbing far above the solar system itself. A machine that can finally look back and photograph our cosmic home from outside the disk we've always been trapped within. And solving that problem requires one of the most terrifying maneuvers ever proposed in astronautics, the Oberth maneuver. The idea sounds completely insane. Instead of firing a spacecraft away from the sun, you deliberately send it toward the sun first, closer and closer and closer, until the spacecraft is falling through space at unimaginable speeds, more than 100 kilometers per second. At that point, deep inside the sun's gravity well, the engines ignite, and suddenly, the physics changes. Because of a principle discovered by Hermann Oberth nearly a century ago, rocket burns become dramatically more powerful at extremely high speeds. The same fuel creates far more energy near the sun than it would in deep space. which means the sun itself becomes the launch pad. A spacecraft dives inward, uses gravity to accelerate, then fires its engines at the perfect moment to violently redirect itself upward out of the solar system. The fall becomes the escape, and scientists believe this may finally allow humanity to reach the unexplored regions above the sun. Some mission concepts take this further using enormous solar sails, massive reflective structures thinner than paper, thousands of square meters wide, powered only by sunlight itself. No fuel, just photons pushing against metallic film for years at a time, slowly tilting the spacecraft higher and higher above the planetary plane. Combined with an Oberth maneuver, such a mission could eventually give humanity its first true view of the solar system from above. And if that day